All right, today's video is going to talk about types of reaction. These are 5 common categories of reactions or patterns of reactions that you've probably already picked up on as you went throughout the last couple homework assignments. So we want to identify what those 5 terms are and what those patterns are so that as we go forward, we can kind of use that pattern to predict how those reactions are going to play out. All right, so the first one that we're going to talk about is called a combination reaction. You can see it already filled in, and that is 2 substances combined to form one new substance. And so we have this kind of generic formula where it says A plus B reacts to form AB. Really what this is showing is that like element A and element B combine together to form one compound. And that's really the cornerstone, the key part to any combination or synthesis reaction, and that is the fact that we only have one product. Things combine together to make only one thing. So an example of a synthesis reaction would be something like sodium and chlorine combine together to form sodium chloride. We've got the element sodium, the element chlorine chemically reacting together to combine and form only one product, sodium chloride. So again, we would say 2Na and then 2NaCl to balance out that reaction. So anytime we see that everything combining is only forming one product, we would call that a combination reaction. And oftentimes we would abbreviate that with like an S for synthesis, or sometimes you'll see it as like a C for combustion, but you'll see why later on. I usually avoid the C. Okay. The second type of reaction we're going to talk about is the opposite to a combination, and that is a decomposition. So that word alone, decomposition, is saying that something is decomposing or breaking down. So we have a single compound is broken down into multiple products. And I say multiple because it's possible for a decomposition to break down. It doesn't always have to be 2 products. It could be 3, could be 4. But again, we have this generic pattern, and that is AB, one reactant compound, is breaking up into its constituent elements. So again, the kind of key idea to identify any decomposition reaction is that there's only one reactant going into this whole process. So if, an example of a decomposition reaction would be something like, let's say we've got aluminum oxide, right? One reactant compound. If it's by itself, it's only going to be decomposing, and so it's going to break down into its elemental components, aluminum and oxygen. But we have to remember that oxygen is one of those 7 diatomic elements, so that's going to be Al plus O2. And so then we'd have to go through and balance out this decomposition reaction, focusing on this 3-2 oxygen balance. So we would have 2 Al2O3s and 3 O2s, so that we have 6 oxygens going in and 6 oxygens coming out. And then those 4 aluminums going in are going to have 4 aluminums coming out. Okay, the next 2 reaction categories, single replacement and double replacement, have very similar patterns, except there's one subtle difference between the two. So for single replacement, an element, usually a metal, so again, note, usually doesn't mean it's always a metal, replaces an ion, usually a cation, in a compound. And so here we've got A element plus BC compound. We have to remember that for these compounds, we always write them as positive, negative. So if A is a metal and metal ions are always positive, then this A is going to replace B and be the positive component in the product compound and produce B by itself. Okay? So if we have an example of something like sodium plus iron 2 chloride, reacts to form, well, we know that the sodium metal is going to replace iron metal, and we're going to form sodium chloride, NaCl, and then it's going to replace iron. So iron's now going to be over here as the element by itself. So a single replacement reaction is identified as an element plus a compound producing an element plus a compound. So for here, this reaction is mostly balanced, except we have 2 chlorines going in, so we need 2 chlorines coming out. So we're going to put a 2 in front of the NaCl, and that means that 2 sodiums also have to enter into the reaction to balance it out. And double replacement, very similar to single replacement, except we now see that we've got 2 compounds, and so we've got 2 ions that are exchanging between 2 compounds. We got AB plus CD, again, positive, negative, positive, negative. And so we can't have 2 positive ions combining together on the product side, and we can't have 2 negative ions combining together. So this positive A is going to bond with this negative D, and then this positive C is going to bond with this negative B to form CB. So it always has to stay in that pattern of positive, negative, positive, negative. And so if we have a double replacement reaction between 2 compounds, we'll say sodium chloride reacting with calcium sulfide. So we've got the positive sodium and the positive calcium, but they're going to exchange position, and the sodium is now going to bond with this negative sulfur, and the calcium is now going to bond with this negative chlorine. So our 2 products are going to be CaCl2, because calcium's plus 2 and chlorine's minus 1, and Na2S, because sodium is plus 1 and sulfur is minus 2. So again, for this reaction, it's unbalanced because we have 1 chlorine going in and 2 chlorines coming out, and 1 sodium going in and 2 sodiums coming out. But for the balanced process, if we have 2 chlorines coming out, that means we need 2 chlorines going in. And by doing that, that gives us the 2 sodiums coming out. And we've got 1 calcium, 1 calcium, 1 sulfur, 1 sulfur, 2 sodiums and 2 chlorines, 2 sodiums and 2 chlorines. And the last category of reaction is one that we've already seen before in our first video notes on balancing chemical equations, and that's what we call a combustion reaction, or what I refer to as a CHO reaction. And that's when we have a hydrocarbon reacts with oxygen to always, bold, all caps, always produce carbon dioxide and water. So anytime we have what's called a hydrocarbon, that's any combination of carbon and hydrogen, so that X and Y could be any number, when it reacts with O2, this particular type of reaction, which looks like it could be a single replacement, always makes the products of CO2 and H2O. That's just the natural formation. Whenever carbon is reacting with oxygen, it forms CO2 most commonly, and whenever hydrogen reacts with oxygen, it always forms that natural, really common molecule, water, or H2O. Right? So if we were to take something like C3H8 and react it with oxygen, just from the combination of those elements, carbon, hydrogen, and oxygen, this is categorized as a combustion reaction. And so the products are always CO2 and H2O. And so all we have to do is take some time to balance out our carbons and our hydrogens, like we did in our first set of notes, and then look at the total oxygen count on the product side. So if I have 3 carbons going in, I need 3 carbons coming out. And if I have 8 hydrogens going in, I need a 4 there so that I have 8 hydrogens coming out. And then if we look at the total oxygen count on the product side, we've got 6 oxygens here, 4 oxygens with the water, a total of 10. So we would need a 5 in front of the O2 to have 10 oxygens going into the reaction. And I kind of goofed a little bit and I started talking about these shorthand codes to identify them. If we have a combination reaction, we can put a capital S or a capital C. Either one of those is fine, combination or synthesis. For decomposition, we're going to identify that shorthand with a capital D. For single and double replacement, we're going to identify that with capital S, capital R for single replacement, capital D, capital R for double replacement. And then for the combustion reactions, we're going to write COM because we've technically got 2 C's and they both start with COMB, but the COMB is going to represent combustion, and then just a capital C is going to represent combination. Okay, so again, this is a little bit more practicing the balancing chemical equations stuff, but now we're going to start identifying and categorizing these chemical equations based on the patterns that we see given the information provided.